Okay, let's continue with the second afternoon talk. So it's a great pleasure that Jörg Teschner came here from Hamburg. So he did his PhD actually also in Hamburg with Hermann Nicolai, and then had a few postdoc positions at Paris, Montpellier, Dublin, and then he spent a long time in Berlin also. And then finally, like 10 years ago roughly, went to Hamburg at DESY and now has a joint professor position at the Department of Mathematics of the University and of DESY Hamburg. And, well, Jörg is an expert on integrability, and that's also the reason why we invited him today. Because we've heard in the introduction by Jakob that while Thirring worked on a lot of subjects, one, of course, was the Thirring model, an early example of some integrable theory, and now it's great to see what happened to the field of integrability. It's a huge subject with beautiful structures, part of which can be seen as generalizations or extensions of the Thirring model. And so I'm looking forward very much to your overview of the uses of integrability.
Okay, yeah, thank you very much for the kind introduction, and thank you very much for the invitation to speak here at this conference. It's a great honor. I'm very happy. I actually never met Walter Thirring. That's too bad. I'm maybe a little bit too young, and but in any case, well, in particular, preparing this talk made me aware of how much I'm actually under his influence, and how much of what I'm interested in is part of his legacy. And to some other, I mean, to mention another aspect, how much sort of the motivations that, well, were motivating me to work on integrable models and so on were actually close to those that Walter Thirring had at the time, which was, I think, the, well, earlier phase of his career in the 50s, where then in particular he wrote a famous paper on what is nowadays called the Thirring model, and okay, we will hear a little more about. And yeah, so the idea is, well, not to go very much into the details of this work, but rather give a survey of what happened to the field of integrable models afterwards, what it may be good for, some of the highlights of successes that this has seen, and maybe I want to indicate perhaps also some future directions. But on the other hand, you can also maybe listen to it and view it as a kind of essay on the way, sort of on the indirect and winding ways science sometimes proceeds. And some ideas from one direction then may, combined with other ideas and so on, generate a lot of interesting insights or results and lead to completely surprising new, well, direction of research or results and so on. Okay, so that is roughly what I have in mind. And yeah, roughly speaking, the ultimate question which motivates this line of research is something as what I put here on the slide. What can we do in theoretical physics when we're facing a jungle, something which seems completely impenetrable, completely wild, hopeless, and so on? Then, yeah, you have to find a good point where you may enter, at least a little bit. I mean, at least to get some idea of how it looks like will be then already great progress. And for the case of quantum field theory, I think this was sort of what Walter Thirring was looking for, and he did find a point of entry, which is what he wrote about, tried to solve, tried to understand in this famous paper of 1958. So, well, the title was A Soluble Relativistic Field Theory. And I'm quoting here from the introduction. I mean, just the first sentences I looked up, and He said, yeah, in spite of the great efforts of many people, the mathematical structure of relativistic quantum fields is still in the dark. This comes from the immense complexity of the problem. And I very much felt I could write it at this time still as is, basically. So this is, and I think, I mean, maybe most of you will be aware to what extent quantum field theory, the study of quantum field theory, is like a jungle. I mean, we have a lot of approximations, partial results, conjectures, and so on. But one of the main problems really is of constructive nature. I mean, we may well characterize it maybe axiomatically what it should be or what it could be. However, apart from free examples, the list of examples where actual quantum field theories have been constructed is small. It's embarrassingly small after all. And secondly, even worse, we want not just to construct them, we also want to understand them. We want to solve them. We want maybe to calculate interesting quantities. And good, there is of course a success story in perturbation theory. Whenever this is applicable, we can calculate quantities with great precision and so on. This is what maybe most of you will be familiar with or have heard of. The technique of Feynman diagrams gives us basically a well-defined recipe to construct for many quantum field theories a formal expansion in some coupling constants where the terms are defined or calculated ideally in terms of some integrals with known integrands. However, of course, we know very well this cannot be the end of the story. The problem is really to construct them beyond perturbation theory, or that the perturbation theory gives us a formal series. We know in most cases it is not going to be convergent. This leads us to expect there are important non-perturbative effects we never see in this way, or which are very hard to see in this way, and so on. We expect interesting phenomena, like sort of, this is this like nice picture which I found when searching for pictures on Landweber's webpage. I stole it from there, which is from some lattice simulations of quarks being bound together by the strong interactions, the forces of glue, and which are believed to be inseparable by the effect of confinement. And this is something that we have no mathematical control on at this stage. So there's a lot we would like to understand, but what we can understand and what we can understand with mathematical precision is pretty small. And yeah, so I think, well, that's the jungle. I wanted to introduce to the jungle. And well, on the other hand, yeah, there's something funny which will come up over and over again here in this field, namely a very strong tension between what we would like to do, what we're able to do, and what we think should be possible to do. So this is very, like, sometimes very far from one another. Okay, so here is the model that Walter Thirring proposed, in fact a generalization thereof, which, well, for future use I shall introduce immediately. Namely, it's in 2 dimensions, a quantum field theory in 2 dimensions, which has as degrees of freedom a Dirac fermion. And I just wrote the action, which has some kinetic term. The mass term was what in the original paper of Walter Thirring was not considered. It was set to 0. The interesting bit is, of course, that it has a 4 Fermi interaction. So therefore, it's not a free theory. And yeah, Walter Thirring's hope was that nevertheless, from this very simplified model, which was not much motivated by like phenomenological or quantum or really particle physics considerations, one can nevertheless learn something about this strange world, this difficult world of quantum field theories. And, well, there is of course an enormous history which I shall not even try to summarize. So, I mean, the attempt, and Walter Thirring made some decisive steps towards it, was to solve it, and then from the solution to learn something on the effects that one can have, the effects that may be unexpected in such theories. So there was a long series of efforts devoted to the construction and or solution of the theory, which is defined, at least in perturbation theory. So from this action, for example, one could develop a perturbation theory in this coupling constant which stands in front here of these interaction terms. So some formal series in powers of G. This is a more or less standard part of quantum field theoretical knowledge, textbook part. But yeah, of course, the goal was to be exact and non-perturbative in this parameter. I mean, to have G as an actual parameter and to understand the dependence of all results on this parameter. And so I put here some of the names which have contributed importantly to, in particular, the efforts to construct this theory. I will not go through sort of who did what and so on. That may not be, I mean, it's also a different talk, basically. It's not the direction I want to go. I just want to mention that actually it took almost 50 years until the quantum field theory with this Lagrangian has been constructed rigorously. So that's some paper from 2007 by Benfatto, Falco, and Mastropietro. So already this, well, I take it as an interesting observation in its own right. All right, so however here, maybe it's the time to quote another few sentences from the introduction of Walter Thirring's paper, which basically formulates his motivations for studying this model in a nice way. I felt when reading it, I could not have said it better. The merit this model may have is more of pedagogical nature, since it shows what a relativistic theory can look like. Furthermore, it can serve as a testing ground for field theorists. In the past, several conjectures about the behavior of relativistic field theories have been made. I'm jumping over one sentence. Since intuition is likely to fail in regions where one has no experience, it would increase the credibility of these conjectures if they could be demonstrated to be true in the simplified case. And I think this is basically what one could formulate as a kind of, yeah, I mean, it in some sense formulates very nicely the motivation for studying integrable models, very specialized, very simplified models, which, however, nevertheless may teach us something valuable about what kind of phenomena to expect in the jungle. Let me anticipate perhaps one reason why this may be so. The phenomenon of integrability, we will discuss it a little more in a moment. It exhibits hidden structures, hidden symmetries, or extra conserved quantities and so on that one does not easily see when looking at the Lagrangian. So there are some very strong and profound mathematical structures which basically give us the mathematical control or give over, for example, certain observable quantities, correlation functions, scattering amplitudes, and so on, that is usually lacking in more general quantum field theories. However, so this is very special. I mean, integrability, no doubt, is a very special phenomenon which is highly non-generic. So, of course, a standard objection to this line of thought or this line of research is, I mean, how can you hope to learn something about more realistic theories in this way? In some sense, the answer is, yeah, we do not really hope to learn everything about the realistic theories. However, in particular, for example, what we can hope to learn is, I mean, if we would look at this theory just from the conventional point of view, it will have all the problems that other quantum field theories also have. So then we can compare. So we can just try to go ahead and try to go as far as we can with the standard methods, but then we also use what the extra features coming with integrability tell us, and thereby we can learn about sort of how the usual problems, at least in this case, are resolved. And this may very well be something of more general nature that is behind that, or that we learn in this way. There's other motivation which I will discuss on the way. All right, but let me also mention sort of the second main theme of the talk, or let me introduce it here right now. It is then something which came after, well, a couple of years. It was, I think, 73 after Walter Thirring's paper, which is a very striking conjecture relating the Thirring model to another quantum field theory on first sight of completely different nature. So that is the famous duality conjecture of Sidney Coleman, who conjectured or presented quite non-trivial evidence for the conjecture that this theory is equivalent, in a sense that I will try to make a little more precise in a moment, to the Sine-Gordon model, which is a two-dimensional quantum field theory as well. However, it only has a bosonic field as its degree of freedom. A single bosonic field now with an interaction term of this type with a cosine type interaction. There's a little typo, mu should be mu, so the Greek letter. Sorry about that. Good, so this duality, I mean, okay, let's recall the main coupling constant here was this G. This controls the strength of the interaction, so this is what in particular appears in powers in a perturbative expansion. Here we see two types of parameters. One is called mu. It's a kind of mass parameter. It is not the one we're mostly interested in here for this duality, but also there is a parameter beta, which if we would rescale phi, we would identify beta squared basically with a Planck's constant, which is the parameter controlling quantum effects in semi-classical approximations. So this is the parameter of main interest here. And the duality that Coleman conjectured would be relating these two parameters in this simple and remarkable way. So G over pi is 1 over 2b squared minus 1 beta squared, beta being the parameter of the Sine-Gordon model. So what this means is indeed, well, I could probably spend a whole talk on all this, but it is truly striking. It means that, for example, the point where this vanishes, which is where the interaction term here vanishes, where this theory is weakly coupled or just free, this will be a point, well, it's the point where beta squared is 1/2, obviously. So that is a point where this here is deeply quantum. So where quantum effects are absolutely crucial and we have no hope whatsoever to apply semi-classical approximation or standard perturbative techniques for the Sine-Gordon model, and vice versa. The two what? Mu's? Oh, yeah, that is also bad. No, okay, so maybe just delete U, so then it's just the mass parameter M that we have there in front of the term. Okay, so, well, what means duality? So what does it mean that one theory, which looks very different, in particular, which has fermionic degrees of freedom, can be dual to a theory with purely bosonic degrees of freedom? I have to be rough, as I have to be throughout the talk. But according to, say, Osterwalder-Schrader reconstruction and so on, we could think of a quantum field theory as being characterized by the whole collection of its Schwinger functions, which are vacuum expectation values in Euclidean signature. So it's the set of all correlation functions where x1 and xn are points in two-dimensional space-time, and phi's are the fields of the theory. Well, here, I would like to think of them, one way to think of them to make it precise is to think of them as being operators, maybe with suitably time-ordered, Euclidean time-ordered arguments such that this actually has an interpretation as an vacuum expectation value of a time-ordered product of some operators, which I can define non-perturbatively. So with B should be beta, well, that is, and mu being just parameters which I can assign finite values. So in the ideal world, I would hope to be able, of course, when I construct a quantum field theory, then it should be a construction of really functions of the positions in space-time where local fields are inserted, at least in the Euclidean version of quantum field theory, and then of all the parameters I have, which here would be m or mu and beta. And duality means is that this object, when I send the parameter beta here to 0, has at least an asymptotic expansion. I can probably not hope more, but an asymptotic expansion in powers of beta, probably it will be beta squared in this case, which is defined by basically standard quantum field theory techniques using this action. If I represent all of these fields or operators here as suitable functions or functionals, local functionals of the basic field phi. Of course, there's a lot of difficulties which can go into this. In particular, there may be field renormalizations necessary and so on. And there may be dependence on the choice of a scheme. The statement would be, there is a non-perturbative definition of correlation functions, and then there exists in the perturbative expansion a choice of scheme such that the perturbative expansion of a more or less standard type defined from the action coincide with the asymptotic expansion of an actual function. So this would be supposed to be the case using sine-Gordon action when beta is be sent to 0, which is, after all, playing the role of Planck's constant for sine-Gordon theory. And the same should be true when we expand around g equals to 0, which is a different point. It does not happen at the same place thanks to the relation of these parameters. So the expansion around g equals to 0 would be defined by the action of the massive Thirring model, this one here. And again, of course, then we have to replace the fields by suitable functions or functionals of the basic fields of the Thirring model, which are psi and psi bar. What this implies is, of course, that the statement of duality always needs to have also a dictionary between the fields of the theory, so that what is here appearing as an observable or as a field then must have two representations, which in the duality, so one in terms of phi and one in terms of psi, which in the duality get identified with one another. So that is basically a duality map which relates observables in one theory, sine-Gordon model, to observables in the Thirring model. Another way of saying it is this: is if I simply ask, can I represent then the resulting theory in terms of some algebra of local operators and so on, maybe realized on a Hilbert space, that then the resulting algebra of operators, which I would ideally like to define from Lagrangian representations like this, in the two theories would turn out to coincide. All right, so that is the famous duality conjecture. I tried to make it a little more precise, although the limitations are obvious. Okay, so this duality, as well, I think most of you know, is truly striking, because what it does is, there is a heuristic which, of course, was motivating Coleman and others to find it. It was observed, of course, for sine-Gordon theory for a while, that it has a classical solutions of soliton type. So these look like, if this here is the spatial direction, and this is the field phi, then this will look like kinks, something like that, maybe somewhat poorly drawn, where then energy, which is coming with a gradient, is localized in a particular region. This does not contribute to the energy, and basically this interpolates between, between values of phi given by the periodicity of this cosine potential. So these are classical field configurations which have a lot more energy or a lot more mass than the field configurations that we would quantize in the perturbative treatment of the sine-Gordon theory, where we have, say, this, what did I have? I had the cosine potential. So then the standard perturbation theory would be expansion around the minimum, so small vibrations around that minimum would be the particles one would study in the usual perturbative treatment of the Sine-Gordon quantum field theory. These are light particles, and solitons as classical configurations have a rather large mass compared to that. However, what was already known by semi-classical consideration is that the mass of these solitons is beta dependent. And so the intuition with this duality is that, in fact, when we turn this parameter beta to, well, the value where it becomes near beta squared equals 1/2, then the solitons will represent actual states in the Hilbert space of the theory, and the duality to the Thirring model would work like that these become the states created by the fermionic fields of the Thirring model. So that is sort of the intuitive picture which goes with that, which explains a little bit how this can happen, that something which has fermionic degrees of freedom is equivalent to something that only has bosonic degrees of freedom, which of course on the first sight is just crazy. It seems these theories can have nothing to do with one another just on the basis of this observation. So I think in this sense maybe, so this in many respects I think is quite non-intuitive that such a thing can happen. Here we see why, we can start understanding why, but that maybe is, for example, what you could have in mind when reading a sentence like, since intuition is likely to fail, and so on, that Walter Thirring put into the motivations for his work. By now, there is a full proof of the duality given by the same authors that constructed the Thirring model, and it was, of course, necessary to construct it in the first place, so one had to build on the other, obviously, and they were using methods of constructive field theory. So that is, of course, a great success, I would say, of that direction of research, but that is not the topic of the talk here. So what had been done over the years on that model was to try to use integrability in order to, well, to test this duality, maybe to understand it better, and perhaps to set up a program which could also ultimately prove it. And it is quite complementary in what it achieved and what it failed to achieve compared to what I just mentioned, namely the approach using constructive field theory. So in particular, it provides a lot of detailed information for sure, and with this going a lot of support for the Coleman duality, but okay, as I will state also, in a moment, it does not manage to give a proof, but it gives other things which are valuable. I mean, in particular, really a very detailed quantitative understanding of both models. So let me go through, I mean, here, as in all of the talk, I have to be very schematic. Let me go through sort of the main steps in the program, that have been pursued and that have been realized to a large extent. So first of all, we believe to completely know the S matrix of massive Thirring model or Sine-Gordon theory. Well, based on the observation or the Ansatz, if you wish, that the S matrix, if it is integrable, should factorize completely into 2x2 scatterings, so 2 particles going into 2 particles. If you have n particles coming in, you will have n particles going out, but all the scattering process can be represented as a product of 2x2 scattering processes. That is a large simplification entirely due to integrability. And if this is so, if one has good reason to believe that this is so, then one can characterize the mathematical properties of the S matrix elements, which are down to a 2x2 matrix. One can characterize the mathematical properties by a set of axioms, basically, which was formulated by, well, many people. I just put here some of the most, I think, well, some of the most important names going with it, but I'm certainly missing many others where one can, of course, debate long for who's important, whose contribution was perhaps more important than anybody others, and so on. I have no chance to go into that. The point is, okay, there's axioms for the factorized scattering matrices of the integrable quantum field theories. And you have to plug in certain informations about what is the particle content, what type of excitations you can have. So, for example, whether you have fermions, how many species of fermions you have, and so on. And then you can look for a solution. And that was, well, a certain industry of looking for solutions. And there exists a solution which is basically tailor-made for the model at hand, Sine-Gordon or massive Thirring, which was found by, I think Karofsky, and then a little later by Zomlotrikovs. And then what people did, very honestly, is of course to really justify the claim that this is the correct S matrix, you have to check it against just standard perturbation theory, which was done in some detail also by these people and others. So both these proposed, I mean, it is really conceptually a conjecture. Why? It uses two things. It uses the very existence of the theory, which you first should show, and it uses the assumption that whatever you have constructed is going to be integrable. In this integrable model approach, of course, what you're ultimately going to do is to reverse the logic, to assume the theory is integrable, and then use all the structures and simplifications to set up a program for the possible construction of the theory. This brings me to the next step. So, okay, S matrix, we believe is completely known. There's a formula that I could have written here, which is completely precise and which would fit easily on like half a transparency, but it would maybe not so illuminating. There is a formula, and this formula has been checked in detail against perturbative calculations in this theory. So therefore, well, I think the very least one has to agree on is it is strongly supported by all available evidence, but okay, in the end of the day, one cannot call it a theorem. What one can study next after having understood the S matrix is information about local fields encoded in what is called form factors, which are the matrix elements, well, either of a local field between arbitrary in and out states, or it reduces to, well, the matrix element of a local field between vacuum and an arbitrary number of in states, say. So these are, of course, standard objects to be considered in quantum field theory. And one can try to find them. In fact, one has succeeded to find them very explicitly for this particular quantum field theory at hand, Sine-Gordon massive Thirring. The way it works, very roughly, is as follows. People have derived necessary and potentially sufficient conditions. I will comment on potentially in a moment, for the thing which would simply represent then correlation functions of local fields like this, so two local fields of the same type, here assumed for just simplicity of writing a formula to be Hermitian, as something that is simply represented by summing over all intermediate states, which we can take to be, in our case, the scattering states, that is asymptotic particle states that, well, go out to infinity. So just by inserting a complete set of asymptotic states of this type, represented as asymptotic particle excitations, you would be led to represent, say, a two-point function of two local Hermitian fields or operators in this form, where the crucial bit which appears here is exactly the form factor, what we have defined up here. It appears here to the absolute value squared because of this assumption with a Hermitian field and so on. Otherwise, I would have some form factor for one of the fields and some other form factor for another of the fields. And then here appears basically something describing the propagation in between, so some factor e to the minus mr cosh theta I, where theta I, well, are suitable parameters for the momenta of the asymptotic particles. We don't have to go into much detail about how this is defined. Basically, this is the energy of the particle I, the cosine, and the momentum would be the sinh of the particle of theta I times m. I guess the m should also carry an I here. Okay, so this would be the representation that I could write simply when having all the form factors. Now, if this is so, this of course, and if this here is to satisfy the axioms of quantum field theory, either in Weidmann or Schwinger formulation, then you can try to translate, and people have succeeded to translate, the axioms, the conditions that ensure the physical consistency of the resulting quantum field theory into conditions on these form factors. This is a type of, well, Riemann-Hilbert type problem governing the dependence on these momenta or rapidities theta or p, which appear as the arguments of the form factors. So basically, it characterizes the analytic properties of these objects. So, yeah, axioms like locality and so on basically end up giving conditions on the analytic properties of these objects. In these conditions, there appears the S matrix, because it tells us how to exchange here arguments. In these conditions, there appears the S matrix. So the S matrix basically is given input data, and then with given input data, one can seek solutions of the conditions following from conditions like locality and relativistic invariance, etc., etc. So this gives a set of equations on the form factors with input being the S matrices. And for the case at hand, these conditions have been completely solved. I mean, these are, of course, courageous efforts, and so it's a great success story that people, well, starting from Karofsky, then Fedor-Smirnov's contributions should be mentioned, and many others have contributed to this, that this ultimately led to explicit formulae for these form factors. And thereby, in principle, one does have an approach to the construction of this theory simply via formulae like this. All that one would need to do is, of course, to carry out the summation here over K. So if the summation, it would suffice if anybody would prove, which I admit has not been done yet, that this summation here exists in order to claim that integrability gives a construction of the theory. But here's the point where it is stuck from this point of view. The convergence of this series has not been demonstrated yet. Smirnov claims to have done it in a simplified example. However, in general, I think it is open. If that would be done, if that gap could be closed, then this framework, this form factor bootstrap would give an alternative construction, which has perhaps the advantage of giving much more detailed information, because, I mean, what is clear in any case is that in the S matrix and in these form factors, what this codes is really, well, ultimately all information that one can have about this theory, it's really very detailed information. One can really try to learn a lot from that. And of course, one can do also checks then with these formulae, namely try to compare this against perturbative calculations again using the actions in massive Thirring or Sine-Gordon theory. And wherever this has been done, it worked out. So therefore, in the end of the day, even though there is not yet full rigor achieved here, the confidence that this is really solid and true is rather high. Let me also mention that one can also study the theory in the finite volume, where instead of infinite spatial extension, one is working maybe on a circle that would correspond to periodic boundary conditions of the Sine-Gordon or massive Thirring fields. There's also a lot of work on that. So what one then would be asking for, what is then the first and the first interesting problem would be to determine the spectrum. I mean, in the infinite volume, the spectrum is basically known when one knows the particle excitations and soliton spectrum and so on. But this is much less trivial, much more difficult in the finite volume. But of course, what is known thanks to Lücher and other people's works is that the infinite volume scattering theory has a lot of deep relations to the finite volume spectrum. So anyway, the way it was approached was to cook up an integrable lattice discretization of the theory in the finite volume, giving a beta ansatz description, again, sort of standard techniques of integrable models for the lattice spectrum. And what is quite non-trivial and required a non-trivial rewriting of the beta ansatz equation in terms of nonlinear integral equations is the fact that there exists a very well-defined, in fact quite simple continuum limit of the equations characterizing the spectrum, characterizing, for example, energy eigenvalues in this theory. So the equations, the nonlinear integral equations describing the spectrum on the lattice do have a well-defined continuum limit, therefore give a prediction for nonlinear integral equations describing the spectrum in the continuum theory. So it gives a, well, not an explicit formula. This is highly non-trivial transcendental information in this dependence of the, I mean, what we're talking about are then functions, not only of the parameters m for mass and beta for the coupling constant, but also, for example, of the length of the circle. If one has a circle of circumference r, then all the eigenvalues will depend very sensitively on how long the circumference of the circle is. So one needs to calculate for each and every eigenstate the functional dependence on at least these three parameters, and this is what these nonlinear integral equations do. So one would hardly expect an absolutely explicit answer. However, this description in terms of nonlinear integral equation turns out to be numerically very efficient. So you can solve it on a computer, spitting out the numbers to very high accuracy. So in some sense, some people like to say that these nonlinear integral equations defining the spectrum, I heard from Werner Nahm that these define the special functions of 21st century, because it is functions with very good analytic properties which you just define in a more intricate way than using integral representations or alike. They're defined by the iterative procedure solving nonlinear integral equations. Anyway, this is a little bit going another direction. I just wanted to mention that also here one can make various checks, and these are very non-trivial, quantitative, detailed checks about limits of the answer. So, for example, in the infrared limit, one can show that the S matrix is correctly reproduced in great detail. In the UV limit, one can compare to the CFT and to these Lagrangian representations also in some detail and so on. So all this has worked out nicely, giving us a lot of information and high confidence that all this is correct. Well, actually, maybe I should go just quickly over this example, a further example of what this integrability-based approach has achieved. I was just trying to put it here, for the sake of illustration. Of course, there's no point here going into the details of these formulae or to try to absorb the formulae here. It just wants to say that there is conjectures based on this, or results in this framework of the integrable bootstrap for the one-point function of local fields, like exponential fields. So the vacuum expectation values of such fields. There's a closed formula, right? So here it's written down. You can trace sort of how the parameters enter, but the details won't matter here. And this is something a formula that Lukyanov and Zonotrikov have proposed, based, of course, on all the results I've been discussing before. And again, the way it works, you see here, simply what I think I want to stress here is, that there's really a lot of detailed information contained in it, in the dependence on parameter beta here, and it's here, and so on. The dependence on the charge here of this field A, that is here, and so on. So it's quite, it's it's not my result, so I can say I find it quite impressive and then one can actually check. So one can, for example, try to expand this in powers of beta and check against perturbation theory. And these authors have done such checks, and it works in a detailed, precise way. There are funny transcendental factors and numbers appearing and so on. It works in full detail. Also, massive Thirring perturbation theory works out, or at some particular values of parameters, one can really try to check that the simplification that occurs in this formula can be matched with some quite non-trivial calculations that one can make when, well, actually the massive Thirring model gets free, when this term here is absent. Because then when it is free, then it turns out this quantity here can be calculated as a trace, and it gives in detail this answer which exactly matches the specialization here. So this is just to impress you a little bit that how sort of finely these things work out, and how non-trivial sort of the evidence that these results give is ultimately, although I also want to draw your attention to this tension that there is. Ultimately, this is based on conjectures. Conjecture that the theory exists, that it is integrable. Okay, so that is basically here again summarized. Sort of the state of affairs, as far as I understand it, is, although the integrability of the Thirring model, to be fully honest and rigorous, one should call it ultimately still a conjecture. If it holds, then it gives extremely detailed information on the various physical quantities, and it has passed, really enormous amount of checks against perturbation theory and other checks. It does not yet give a rigorous construction, but, well, the potential is still there that, for example, this convergence issue is solved, and then it does give a construction. Well, it could also come from the lattice by really fully controlling the convergence of the continuum limit in the integrable lattice discretization that people have studied. So that, I think, is the state of affairs here. Nevertheless, I think to my mind, but that let me propose you as a very personal conclusion, there's really no good reason to doubt that all these results here coming from integrable are ultimately correct. The constructive methods I've mentioned, they have definite strength in giving rigorous proofs of existence, and it has given a rigorous proof of Coleman's duality relatively recently. But I think it is fair to say that they have as a drawback not yet reached the stage that they would give as detailed information as integrability does. So there is a clear trade-off, which is, I think, normal, that some approaches are good for some questions and for obtaining some types of informations, and others are stronger for giving other types of information. And usually you cannot have all, right? So that's what we have to learn in life, that we cannot have all, even if we want so. Okay. Well, I'm slower than I thought, but anyway, maybe the rest I can be a little more quick. Well, now, how does history proceed? So I think it is true that this first example of a duality, where people have seen this phenomenon of what can happen when you go to strong coupling in a quantum field theory, that it can completely change its nature and can look completely different. Once you've seen it working in one example, of course, you start looking for others where you find similar phenomena. And as a matter of fact, this phenomenon is maybe not so exotic as it may seem. By now, there's a rather large list of other examples where such phenomena exist or have been conjectured, and again, there's a certain industry of checking them, and of course they have been checked to rather varying extents. In some cases, for example, one can again use integrability and check them very non-trivially. In others, it is very much like a guess at the moment. So here I just flash, maybe very briefly, one example that I find very striking in some other respect. It is, in a sense, an extension of the massive Thirring Sine-Gordon duality, where you simply take some more complicated theory, which now has a Fermionic degree of freedom. Actually, I could have written this in a way such that this here looks like just massive Thirring. I'm just using little different notations for the spinors, for the fermions. But now it is coupled to a boson, phi 1. So one boson, one fermion now. And the statement is that in this case, a duality which, well, is known, is believed to exist and which was checked by integrabilities, that in this case, the dual representation, which would be at the place of Sine-Gordon theory, is in fact of sigma model type. So here we see basically something of the form, some integral d2x g mu nu of x, and then well, actually, maybe I use other indices here, mn d mu x mu of little x, and d nu, this wanted to be m, and the n, and with some eta mu nu. That is what is called sigma model action, which is defined by putting a metric, and x would be a map from, say, in this case, just two-dimensional space into some other space, a target space, called target space, which here would also be two-dimensional. It is parameterized by the fields here, phi 1, phi 2, in the place of x mu and, well, xm and xn. This here would give the non-vanishing metric components of the metric g mu nu. So this is of a sigma model type, as, for example, appears in string theory. So that the model, which just has some fermions, some boson, and then some potential terms, some interactions, like for Fermi interaction, and some potential here, some coupling fermion to this, that this is just equivalent to a purely bosonic sigma model, I find another quite striking example of the duality. So I'm stressing this because I think it really is something which we need to digest much more, this multifaceted nature of quantum field theory, that the question ultimately is, we want to understand what quantum field theory really is, and if quantum field theory can have such different guises, such different representations, yeah, it poses certain challenges, and also it gives certain hints. Okay, so now I have to become more and more vague and schematic. What I want to mention, at least, is that these results, that the story doesn't stop there. And furthermore, one of the main points is, of course, that this phenomenon of duality is not something which is peculiar to low-dimensional quantum field theory. By now, there is very good evidence and a certain list of more or less well-checked duality conjectures, even for four-dimensional quantum field theories. One class of examples is what is usually referred to as S-duality in gauge theories, or the examples where this is believed to be true and where this has been checked to some extent. These are those which have supersymmetry, which is the decisive simplifying feature giving us calculational control for these cases. So the rough statement of the duality then is that there is a supersymmetric gauge theory with action S1. So that is again an ordinary action for four-dimensional quantum field theory containing fermions, containing bosons. Of course, there are relations ensuring that supersymmetry is there. But it has, for example, gauge fields, and the gauge fields have the usual couplings among themselves with a coupling G1. And the statement is of the type that if this coupling is getting very large, that there is ultimately an equivalent description of this so defined abstract quantum field theory in terms of another action S2 of G2 with another coupling constant G2, which of course ultimately must be in some functional relation with G1. They must have the same set of parameters, these theories. However, at weak coupling, so when G1 is large, then this function G2 of G1 must give something small, such that in this regime, I better use the action S2 in order to set up a perturbative expansion for this theory. So that is I mean, in some sense, of course, I could just have referred back to how I tried to make a little more precise the statement of duality for the Sine-Gordon massive Thirring case. Here, however, I just want to stress, yeah, these are ordinary four-dimensional quantum field theories with gauge fields and then supersymmetric partners, and they have then these couplings which are related here. And it is a strong weak coupling duality. That is the nature of those. And basically, yeah, to state this, you have to produce lists of how action S1 looks like and how action S2 looks like, and that formulates then the conjecture. So such conjectures go back to Montin and Olive in '78, and historically a boost came then in around '94 through works of Sen, the famous works of Seiberg and Witten. There was also related works of Waffer and Witten, and it has more recently seen a second wave of generalizations, but also of much more refined tests, thanks to work of Gaiotto, Moore-Neitzke, and so on. So the situation about this, there is by now a long list of duality conjectures, but as long as these theories have not been constructed, of course, these remain conjectures. And the strong point perhaps one can mention is that they have passed highly non-trivial quantitative checks due to the fact that special quantities can be calculated through a new method called localization. In this form do the work of Pestun, Vasily Pestun, who's now a professor at IHES, and relation to two-dimensional quantum field theory again. It was discovered by Alde, Gaiotto, Tachikawa. So let me be clear, this is not about the theory as a whole. However, special quantities can be calculated exactly, and for these special quantities one can check these conjectures exactly, also using some CFT results, and that is the only place where here in this talk a little bit of my work in this field appears. So that is also, well, giving checks, not more, but on the other hand, there are checks about rather detailed information, so in some sense you can find them compelling, or depending on your attitude, not. Last but not least, yeah, maybe I should come to some good end. I want to mention another class of dualities which are perhaps the most striking that we think we know. Because, yeah, really the point is, I think they pose challenges on quantum field theory, and in particular on anybody who is trying to be mathematically precise in quantum field theory. So there is reasons to believe these funny conjectures, which I'm trying to stress, but on the other hand, we seem to be pretty far from actually proving them at the moment. So this class of conjectures I quickly want to discuss in the remaining few minutes. These are called large N dualities. So the idea, going back to 't Hooft, was to regard the rank N of the gauge group of a gauge theory as a parameter and try to play with it. So far we've seen parameters like coupling constants, but why not use this as a parameter and maybe see if it is large, whether simplifications occur, and a better understanding or some alternative representation may be possible. Okay, so yeah, I cannot explain what 't Hooft did here, but roughly speaking, he was reorganizing the diagrammatic expansion as an expansion in inverse power of this rank squared of the gauge group. And the key observation was that the Feynman diagrams in this reorganized way were in were in correspondence. So classes of Feynman diagrams here were in the correspondence with triangulations of two-dimensional surfaces, which are topologically characterized by the genus G, the number of handles. So, I mean, we're thinking now of something looking like this, which would be G equals 2, two-dimensional surface. So the topological types basically classify here the Feynman diagrams having the same powers of n. That was 't Hooft's observation. And this is what then invites for a comparison with string theory, because the resulting structure of the perturbative expansion in this reorganized form, it was noted, resembles the perturbative expansion of a string theory. Okay, so what is this very briefly? I mean, the recipe for defining amplitudes in a string theory which is the theory of extended objects moving in a higher dimensional space-time, is it uses some auxiliary two-dimensional quantum field theory and its correlation functions as the main building blocks for the definition of scattering amplitudes. So, well, these fields phi, okay, they should be thought of as carrying the dependence on the momenta K1, for example. So this depends on K1 secretly. I've not written this here in the notations. So there is an operator associated maybe to an excitation with momentum K1 and so on. So then the structure of scattering amplitudes for these extended objects. So again, I can ask, I send in any number of these extended objects, something happens, and then they go out. So the recipe for constructing them is by integrating over the number of parameters of this Riemann surface, this two-dimensional surface sigma, which is just collectively denoted M, the correlation function of an auxiliary quantum field theory on that two-dimensional surface. And the typical idea is that these correlation functions are usually defined using nonlinear sigma models, that is, using actions of the type we have seen. Now, what was not clear at all after 't Hooft's observation was, is there a sigma model? Is there some action like this that with this recipe applied to this sigma model, it would reproduce the large N expansion of gauge theories? So in this sense, it was just sort of a crazy observation, something which was not actually clear whether it has any meaning or was just a funny, like diagrammatic coincidence. Yeah, and what is called ADS-CFT correspondence, as discovered by Maldacena, is a precise version of this relationship. It would say that in this sense, for a particular supersymmetric Young-Mills theory, in this limit where n goes to infinity, this procedure would work if one uses as input here, well, for the definition of the correlation function, the input here is the metric on the target space of the sigma model. So if you put here the metric defined by saying, yeah, that you have as target space ADS5 cross S5, which has a standard metric on it, if you plug this metric in, then the statement would be that this recipe here reproduces, in fact, exactly the terms of order, say, n to some power in the perturbation theory of this four-dimensional interacting quantum field theory in the planar limit. There's a relation of parameters, which maybe I just skip. It is such that the 't Hooft coupling, which is a combination of the Young-Mills coupling and the number of colors, which we keep fixed when n goes to infinity, this is related to the curvature radius of the ADS space. So that is the main relation that goes into this duality. So, I mean, I'm not expecting to find many great fans of string theory here in the audience. However, I think if you take this series, then you have to conclude that string theory on at least ADS spaces is in fact part of quantum field theory. It's part of the study of quantum field theory, namely gauge theories in the limit where we have a large number of colors. Okay, so actually I'm running out of time. This slide was meant to summarize the available evidence, which thanks to integrability, I think has become also quite strong and compelling. I mean, what has been applied to this problem is a variant of this S-matrix bootstrap program, now tailored for this class of theories, which are, of course, somewhat more complicated than Sine-Gordon. But this has been applied in a, well, long series of efforts. There are many people contributing to it: Staudacher, Minahan, Zarembo, Baisat, Gromov, Fiera, and so on. I did not put them here on the slide. So basically, yeah, the highlights of this program are it gives an exact formula for the S-matrix again. There is an exact formula, or, well, it is basically representing, no, it basically gives an exact explicit formula for the S-matrix, which has a matrix part and then some transcendental part, which is quite non-trivial, defined as solution of certain integral equations. But that is known, and it defines basically the S-matrix as a function of this coupling that remains, the coupling being here this 't Hooft coupling lambda, for all values of lambda. Using this, one has set up a program to determine the finite volume spectrum of the sigma model, which in the gauge theory context would be anomalous dimensions of gauge theory operators. And also for this by now, as a culminating achievement of a long series of efforts, one has found a description in terms of nonlinear integral equations, or an alternative one in terms of a special type of Riemann-Hilbert type problem. So it puts the problem to calculate, for example, anomalous dimensions as exact functions of the 't Hooft coupling into a problem of complex analysis. And then what you can do is just from these results, for example, you can take special operators and calculate the perturbative expansion in powers of this 't Hooft coupling, here rescaled by 4 pi squared. And it gives something like that, right? So you see here zeta values and funny constants and so on. So this was a prediction coming from this integrability approach. It was a prediction until people actually sat down and did a for loop computation, say, in the gauge theory, which is a lot of work, you can imagine. For loop in gauge theory is not so easy. But people did this honestly and really with the standard methods. And it reproduced exactly this result. So, okay, I don't know. It is a non-trivial check, I would say. This part here so far is beyond the ability of what can be done in perturbation, in gauge theory, perturbation theory, but Kochemsky and company have, with some other method, been able to verify this prediction coming from integrability. So at least, yeah, I mean, I'm just mentioning it here to basically pose challenges for this interaction. Integrability, mathematical quantum field theory, and so on for the future. So I think this idea here deserves to be taken seriously, and in particular what we learn is that this subject of string theory, in fact, is inevitable subject, a part of the subject of quantum field theory. All right, so I'm coming to the end. I'm actually a little bit over time, but maybe I can quickly mention the last words, coming back to Walter Thirring. So part of, I mean, integrability, the study of integrable models, I would understand as part of Walter Thirring's legacy, and it has a lot of success, led to a lot of success in regions where we have no experience. I mentioned these examples, maybe this I can skip, and so yeah, the message or the moral of the story was supposed to be that even simplified models may teach us a lot. They may have hidden features allowing detailed analysis, but may have the usual, or usually will have the same problem, the usual problems when approached by conventional methods. So you can hope to get insights into non-intuitive phenomena or insights on how the usual problems might get resolved. And yeah, what I think what this should be able to do for us in the future would be to understand better, for example, how these dualities come about, why they hold in the first place. One can use them to check the necessity for new concepts or the relevance of new concepts. So, for example, the question is, in the context of theories of quantum gravity, say, like string theory is, should we base it on the usual notion of Riemannian geometry, or do we need deformed, modified concepts thereof? I think it would be good to have soluble examples where we can see it is in fact necessary that we modify our usual notions, and if there was more time I could give ideas in this direction. And maybe, yeah, also we need to develop much better calculational tools, and then, like in the example here that I quickly mentioned, this would give benchmarks, right? So first was here the integrability prediction, then challenging people to actually calculate to for loops, which otherwise would not have been very well motivated. And it also leads to the development of new techniques, like, for example, here, this one was checked with new techniques, which are not standard perturbation theory. And so I think, yeah, this interplay is what may make it valuable. Good, so I stop here. Thank you.
Thank you very much for this overview, drawing the line from the Thirring model to string theory in the end. any CFT duality. Other questions, comments?
You mentioned that this is Malacino duality only sort of the well-understood part.
Yes.
What about people who try to do QCD dual with black holes in the ADS, CX in the ADS part?
I'm not sure I can give very good comments now in very few words. In fact, I also don't know all that is going on there. So the belief is indeed that there is a large class of generalizations of these dualities which are basically motivated by the same idea. So what motivates this belief is that there is no reason why the mechanism of that 't Hooft basically had already discovered should stop in this simple case. There's no reason why it should not work in other cases as well. However, what is very hard is then really to find the matching pairs of precisely described gauge theory and a precisely described geometric space. So there is maybe with a little less supersymmetry, there are examples. So for n equals to 2, one believes to know what is the corresponding ADS space. So there is a certain industry of finding more general solutions of the 5-dimensional Einstein equations, which would then take the place of ADS space. And it has certain success, and then, good, it gets more and more complicated and maybe less and less controlled, as you can imagine, to find these pairs space to quantum field theory, which would do this job. However, I mean, yeah, it's impossible to really exhaust this, and also I partly may lack sort of the up-to-date knowledge. But so, for example, people are trying to use this in order to at least predict universal features of heavy ion scattering. And there seems to be some success in that. So, I mean, this is pretty far from what is under good mathematical control. However, they do find certain matches of what is observed to what these ideas predict. That's maybe an attempt for a brief answer.
More questions or comments? Okay, if not, then thank you very much again.
Thank you.
We meet again at 4:30.